star.
I was muted. Hello, everybody. Welcome to this month's Astronomy on Tap. Thanks so much for joining us this evening. I hope you got a cold glass of something to sip on. I'm drinking water tonight. No beer, but I look forward to hearing the talks this evening. So to start us off, we're going to be doing some trivia throughout the night, some trivia questions. So I'm going to start us with 2 questions, and then I'll ask a few more throughout the night. And however you want to record your answers, if you want to put them in the comments below this video here, put them on Twitter, Instagram, anything like that, we'll be looking out. Just make sure that you tag us if you are answering the questions on social media. Or if you want to write them all down on a piece of paper, take a picture, post it on your Instagram story, anything like that. We would just love to engage with you and interact with you on social media. So definitely do that for us. So I'll go ahead and share the questions. September trivia. The theme for these questions is seasonal astronomy. And at the very end, I'll go over all the questions and all the answers. So, question number 1. The September equinox occurs on September 19th in 2020, ushering in the fall season in the Northern Hemisphere. On this day, the sun stands directly over Earth's A, North Pole, B, ecliptic, C, equator, or D, South Pole. So you can answer with A, B, C, or D, or the word or phrase or anything like that. Write it down. All prizes are honestly just me giving you a round of applause and maybe a shout out on social media. So, but we do still have merch and things like that. So get into contact with us about that if you would like to purchase anything. Okay? I hope that's enough time. I'm going to go on to the next question. Derived from 2 Latin words, equi and nox, what is the significance of the equinox? A nice little diagram to sort of help you out there. Little short answer question. It's getting intense. I'll read this one more time. Derived from 2 Latin words, equi and nox, what is the significance of the equinox? Okay. So this week's theme, we're talking about instrumentation and the various gadgets that astronomers develop and come up with in order to do their science and do all the observing necessary to learn more about the universe. And so first up this evening, we have Dr. Emily Martin joining us. So Emily, go ahead and welcome.
Hello.
Thanks so much for joining us tonight. How are you?
Doing well. How are you?
I'm doing all right. I really like all the plants behind you, giving a nice little background for you tonight.
Yeah, I'm going full on plant lady during the pandemic. So.
Totally feel that. We're in the process of growing an eggplant, clementines, and sweet potatoes over here. So
wow. Okay, farming. That's awesome.
But anyway, all right. So I'll let you get to it. And
okay. I will start.
enjoy.
Thank
everyone.
you. Okay. start sharing my screen. Okay. Alrighty. All right, so hi everybody. My name is Emily Martin and I'm a postdoc at UC Santa Cruz. And tonight, Connie Rockosi and I are gonna be sharing some about both big and small gadgets or instruments that we build to do the science that we wanna get done. And so tonight, my talk is gonna be about a new instrument coming to Lick Observatory this winter. And it's gonna use a really cool little optics trick to help condense the light from the larger solar system planets to make them small so that we can compare them to exoplanets. And before I get started, I want to acknowledge and thank the National Science Foundation, the Heising-Simons Foundation, and also the UC Observatories for their support of this project. Oops, there we go. Okay. Connie and I also really wanted to give a really big thank you to all of the firefighters who helped save Lick Observatory and who have been putting out fires across Northern California over the past few weeks. It's been a pretty scary time and we came really, really close. As this image shows, you can see the just how close the fire came to some of the observatory buildings. But due to the incredible hard work of everybody working up at Mount Hamilton, none of the residences or the telescopes were lost. And so we're just incredibly grateful for that. All right, so I'm gonna get started with a really iconic photo and some quotes from Carl Sagan about our pale blue dot that we call the planet Earth. So in 1990, as the Voyager 1 spacecraft was leaving our solar system, it turned back around for one last look at Earth. And you can see that there as this tiny little speck, a little less than a pixel of a pale blue dot that looks like it's suspended in a sunbeam. And Carl Sagan said, "The Earth is a very small stage in a vast cosmic arena. Our planet is a lonely speck in the great enveloping cosmic dark." And I just think that is a really nice, beautiful way to put into perspective the tiny little corner of the universe that the Earth takes up. And even though at that time we didn't know of any other exoplanets or any other planets orbiting other stars, we had a pretty good idea that we were going to find some. And in fact, in 1995, only 5 years later, the first exoplanet around another solar type star was found. And today, as of today, we have more than 4,200 confirmed exoplanets. And there's actually thousands more waiting to be confirmed. And we can make a pretty good approximation that on average, there's at least one planet around every star that you can see in the night sky. And about 1 in 5 stars like our sun has a terrestrial planet orbiting it in the habitable zone. So in a potentially place that could be harboring life. So we know that there's thousands and thousands of confirmed exoplanets, and we can actually now start to think about what their atmospheres might be like. We want to study their compositions, and we want to compare them to the other planets in our own solar system so that we can start to understand kind of the vast array of planets and planetary atmospheres. In our own solar system, weather is actually a thing that happens on basically every planet that has an atmosphere. So on Jupiter, for example, you've got the giant red spot. It's a massive storm that's been around for more than 300 years. And you've got also these bands of gas that are swirling around all the time, as well as actually some pretty big cyclones that happen on the poles of Jupiter. On Neptune, shown up here in the upper right-hand corner, Neptune has this really thick atmosphere of helium and hydrogen and helium, and it has these big cloud systems that sweep across the surface at really, really fast speeds, sometimes up to 1,200 miles per hour. And then on Venus, which I'm showing here on the bottom right, not only does Venus have this very deadly atmosphere of a mixture of carbon dioxide with sulfuric acid, but then there actually is this massive polar vortex storm that's happening at the poles. So we know that the weather is something that affects the solar system planets. And we also are pretty sure that this is something that is going to impact all of the exoplanets as well. And we've started to begin to characterize that. And so one of the ways that we've done this is by studying the weather on hot Jupiters. So these are exoplanets planets around other stars that orbit so close to their host star, they're actually going around in an orbit in about 1 day, or even less. And so in this particular example, there's this exoplanet called WASP-43b. And WASP-43b is a Jupiter-sized planet that's so close to its host star that on the on the day side of the planet, it gets really, really hot. But on the night side of the planet, it is not very hot. And that creates this really big temperature gradient across the surface of the atmosphere of the planet that will produce some really interesting weather effects. We've also started taking a crack at studying the weather on exoplanets by studying free-floating planetary mass objects called brown dwarfs. And from our studies of brown dwarfs, we've actually been able to see clouds of things like methane, CO, carbon monoxide, and study how those clouds vary with time. And so if you go back and look at the same object many, many nights in a row, you'll actually see that the cloud patterns are changing and that the signals that we're receiving from that object are changing over time. So we want to eventually be able to do this of comparing exoplanets and the observations that we can take to them with all of the detailed, incredible wealth of information that we have on solar system planets. But there's just one tiny little problem. So here I'm showing you the angular sizes on the night sky, so all shown to scale. So the moon is about 1/2 degree on the night sky. And that's equivalent to 1800 arc seconds. So that's just another unit that we use to measure distance on the sky. And Jupiter is about 45 times smaller than the moon on average from our perspective. And so Jupiter is about 40 arc seconds. And so that's kind of the scaled difference between Jupiter and the moon. And an exoplanet system, if we were to take an image of an exoplanet system on the night sky, the whole entire system, the star and the planets themselves, would actually only take up a couple of arc seconds, which is represented here by this tiny little red dot, which is only 4 pixels across. So we really ultimately have an optics problem that we need to solve. So if I zoom into the exoplanet system and we can compare it side by side with Jupiter, what you can see here is that at the scale of 40 arc seconds, we can actually get incredibly detailed images where we can spatially resolve the bands. We can see the giant red spot on Jupiter. So we can see all of these individual features. The problem with this exoplanet picture is that this particular exoplanet, for example, this one is called HR 8799c, that's its postage stamp. That particular planet is just a single point of light. And so it's very unlikely that we will ever, in our lifetimes, resolve individual spatial features on the surface of an exoplanet. And so comparing these two things gets a little bit tricky. So whenever we want to study the composition or the atmospheric makeup of anything in the night sky, we turn to an astronomical instrument called a spectrograph. And the input to a spectrograph is oftentimes a slit that allows only light from a small amount of the sky into your instrument. And the problem is that if you try to take a spectrum of Jupiter, the image itself of Jupiter is so large that you can't get the entire planet to go into your slit. So it's an optics problem. But if you want to take a spectrum of the entirety of an exo-Jupiter, all you have to do is make sure that that single point of light goes into your spectrograph. And what you get on the other side is really global properties of that exoplanet. So here I'm showing real data of these 2 different planets. So we have Jupiter on the left, and we have HR 8799c on the right. And with Jupiter, what's really fascinating is that depending on where you put your slit, so depending on which portion of the planet that you're looking at, the output spectrum that you observe, where you see all of these dips that represent the presence of various molecules, things like very interesting things like phosphine or deuterated methane, water, that are present in the atmosphere of Jupiter. The appearance, which tells us a lot about the underlying physics of what's going on, varies widely depending on which slit, which portion of Jupiter you're observing. However, with this case of HR 8799c, we're getting the entire global properties of that exoplanet. So we can see that it has water vapor in its atmosphere, it's got methane, and it's got carbon monoxide. And so we want to be able to take the observations, this truly incredible detailed amount of information that we have on planets like Jupiter, and be able to put it into a form that is more directly comparable to the exoplanets that we observe. And so that's where this little optics trick comes in. So our workaround is that we're using a piece of an optic that's called an integrating sphere, and we're going to take the image of Jupiter or the other solar system planets, and we're going to disk integrate it using this integrating sphere to create a very smooth image on the outside. And so the way that an integrating sphere works is it's basically a hollow sphere, and on the inside it's coated with a very highly reflective but diffusive material. So that means that when light hits the surface, it's going to scatter at random angles. And the light is going to reflect many, many times, bouncing all around the sphere many, many times until it gets completely mixed up. And so if you have an image from a telescope that produces this Jupiter image, on the input side, you can see the bands, you can see the giant red spot. On the output side, you basically just get a very smooth, peachy, orangey colored disk. And so that is the light. This global average is much more similar to what we can get with exoplanets. And that is the light that we'll be sending to a spectrograph. And so this is the actual integrating sphere that we bought for the instrument. So it's only an inch. It's not a very large thing at all. It's only an inch in diameter. But you can see the very, very white, highly reflective surface on the inside. And so this instrument is called PEAS, and that stands for the Planet as Exoplanet Analog Spectrograph. And so basically that means we're observing solar system planets as if they were exoplanets. And we're taking all of the same kinds of observations and using the same kinds of techniques that we would use to characterize exoplanets and validating that with what we know to be true about the solar system planets. And so this PEAS project as a whole, this is sort of a global view of what the instrument itself looks like. And so the entire instrument consists of a telescope that is dedicated to just this project. And it will be looking at solar system planets. And it will take the light from those solar system planets and send the bulk of that light into an integrating sphere where it will get globally mixed up. And then we'll take the light from the integrating sphere and feed it via fiber optic cable into a spectrograph, which will then take the spectra and allow us to do the science that we want to do. A small amount of the light will also go into an imaging camera. And so that way we'll be able to have both simultaneous imaging and spectra. So even during these very tricky times during COVID, we've still been able to move forward with this project here at UC Santa Cruz. So this is me standing in our shops up at the UC observatories. And we actually got our shipment of the telescope just about a month ago. And here's the 1/2 meter plane wave telescope mounted on an L500 mount. And I actually have a little video here showing you how gorgeous it is and how quickly it can slew. That means it moves from looking at one target to another. And it's fully automated, just really beautiful, and we're very excited about it. And then to go on the back side of the plane wave telescope, so this is the telescope that you just saw. And on the back side, we have some optics that contain the integrating sphere. So this is a zoom in of the light path from the telescope. And most of the light comes straight into the integrating sphere, and there will be a fiber here that feeds a spectrograph that will sit on our cart. And a small amount of the light will go into an optical imager. And we also have plans to eventually upgrade to an infrared imager as well. And all of our equipment will sit on this rolling pier mount. And we are going to be taking it up to Lick Observatory to Mount Hamilton, actually within about a month or a month and a half, which is pretty exciting. And so PEAS is going to live inside the dome of the Shane telescope at Lick Observatory. That's the big 3-meter telescope at Lick. And so we'll live inside the dome, and then every night we'll wheel out to the parking lot to the east, and we'll observe the southern skies. So that's where all of the planets are in the night sky from our perspective. And then when we're done with our observations, we'll wheel it back inside where it can be protected from the elements. But yeah, so the PEAS science mission is number one, we really want to produce an atlas of solar system planet spectra that we can directly compare to the observations we take of exoplanets. And we hope to then compare those to the known truth, the ground truth that we have from space missions, from historical observations with ground-based and space telescopes, in which we know the atmospheric composition of Jupiter. We know what the atmospheric composition of Venus is, et cetera. We're also going to be producing 2D surface maps of all of the solar system planets. And we're really hopeful that by validating these techniques that we are hoping to use on exoplanets, that we're going to help inform future exoplanet missions as to the best way to build their future instruments. And then we're also going to be taking time series data. So that means every night we're going to come back and we're going to look at the same target over and over and over again. And by doing that, we'll be able to track things like weather patterns in a really dedicated way. And then lastly, we also eventually hope to study the planetary seismology. And so that's like the oscillation mode. So we'll hopefully get to see things like the beating of the solar system planets. So this is some pretty exciting stuff that has been done with Saturn before, as well as other planets. And so we hope to do that. And so this is really exciting. This is a brand new instrument that's coming to Lick Observatory in just a couple of months. And we're very excited about it. Thank you.
A round of applause to you. That was awesome.
Thank you.
And I have been repping PEAS for months now because I have a sticker of the logo on my water bottle. And I loved that without even knowing what you were doing. And now I know what PEAS is, and I'm even more in love with it. It's just the coolest thing. That's really, really awesome.
Thank you.
All right. So we have a question from the audience to ask you. And it reads, does PEAS integrating sphere emulate distance-based effects like redshift to the spectrum from solar system planets, or is stuff like that done separately?
Kind of. So the redshift effects are actually a wavelength effect. And so that's separate. But what PEAS does is it emulates all of the spatial mixing that happens because the exoplanets are so far away. Whenever we're observing them, all we see is a tiny point of light. So all of that light has been, as it's traveling through space, has gotten spatially mixed up from our perspective. And so we can't actually resolve like, oh, this light came from that portion of the planet, or that light came from that portion of the planet. So that's basically what the integrating sphere does.
Oh, and another question. Will you be at Lick running PEAS yourself, or will the Lick staff be in charge of the data collection?
Yeah, good question. So at the beginning of the project, it's probably just going to be me and Andy Skimmer, who's a professor here at UC Santa Cruz that I work very closely with. And eventually we're hoping to get a whole team of students to come help us do our observations. So this is right now we're not expecting the Lick staff to be running anything for us, but they have been very, very helpful, and we're excited to be working alongside them.
Nice. And I have some questions for you as well.
Okay.
When did you know that you wanted to do instrumentation, and when did you start exploring that interest?
Yeah, so I got my start in instrumentation when I was an undergrad at Texas A&M. Whoop. So I worked in the instrumentation lab there, and it was kind of a fluke. Like, I was a physics major and I didn't know what the heck I wanted to do with my life. And I was like, maybe I should try working in a lab. And so I just like emailed a bunch of random people asking if I could help work in a lab over the summer. And one of the people who responded was Jennifer Marshall, who's a professor at Texas A&M. And she was like, yeah, just come check it out, see what you think. And she showed me around the lab, and I was like, oh, this is so cool. Like, I just love everything about it. And yeah, I just had the best time working there. That was my right before my senior year of college. And so I was thinking about applying to grad school, and I was loving what I was doing in the lab so much. I was like, I want to be an instrumentalist forever. Like, I love building things. I love making instruments that can do cool science. And yeah, it was just kind of like a dream to find that.
Nice. Very
Yeah.
cool. And one other question regarding the exoplanets, you're learning about what you do not fully know by comparing it to things we know about our solar system planets. Is there a similar process that we can do with stars?
Ooh. I mean, yes, I think so. Like, I mean, I think that there's actually quite a lot that we don't know about our sun, even though it's the closest star to us. And I know that there are several very large solar observatories, both in space and from the ground, that are looking at the sun all the time to try to better understand that, because it is this just like giant burning ball of gas, but things are happening, and there's magnetic fields, there's all of these other effects that we don't fully understand. But yeah, that's a good question. I don't know.
And then one last question about you. How long have you been in Santa Cruz, and what drew you here?
So I've been in Santa Cruz for about 2 years now, and I moved here for my postdoc after I finished my PhD. And I love everything about Santa Cruz. Like, it's so beautiful. From my apartment, I can walk to the redwoods. I can walk to the beach. It's a great place. I've been very happy here. So, and it's an awesome department. So,
Nice.
yeah.
Thank you so much for
Yeah.
sharing
Thank you
your
for
time
having me.
with us and talking to us this evening.
All right. I'll see you later.
See you. It has also come to my attention that I did not introduce myself. I am Alexandra Mannings, or Alex, if you like. I am a now second year grad student in the department, the Astronomy and Astrophysics department at UCSC. And I'm very, very, very excited to be the new MC for Astronomy on Tap here in Santa Cruz. Yep. Okay. And now for our second speaker, Dr. Connie Rockosi, here to continue us on this journey of learning about instrumentation. How are you doing this evening?
I am doing great and super excited to be here.
Nice. Yes, we're excited to have you. Okay, well, I'll let you have the floor.
All right. Let me. Okay. Emily talked about an instrument that she's working on to make the planets in our solar system smaller. And I'm going to talk about a different project to build a new instrument, or actually part of an instrument. And this one is going to be one to use a surprisingly large piece of silicon to be able to help an instrument see red light better and learn about the universe that way. Why do we want to do that? Well, it turns out that red things in the night sky are almost always rare and super exciting, and they almost always give us a chance to learn something unique about how the universe works. And so catching red light is a way to help us observe new things and learn more about the universe. And one of those things that we are interested in finding when they're really red are quasars, which are giant black holes in galaxies. So we live in a galaxy, the Milky Way, and like almost all other galaxies, we have a giant black hole in the center. And it turns out that some galaxies, their black holes are much, much brighter than ours because they're in the process of swallowing a whole lot of hydrogen gas from that galaxy. And that makes them shine incredibly brightly. And we call those things quasars. And when they're really red, those quasars are incredibly interesting. And that's because the reason that they're so red is that they have been redshifted by the expansion of the universe, so that all their light comes out at these really red wavelengths. And the reason they're so redshifted is because they're incredibly far away. And that in turn means that because they're so far away, the light from these things that we're observing now came from them an incredibly long time ago, surprisingly close, not too very long after the Big Bang, when the universe as we know started it. And one of the reasons we'd like to be able to find these really red quasars and study them is because we'd really like to understand how it is that the universe can put together a gigantic black hole in a great big galaxy so soon after everything started at the Big Bang. But if we're going to figure this out, the first thing we have to do is to build instruments that are really good at catching really red light so we can find them. So how do we do that? How do we get good at catching really red light? Well, we're going to use a really big telescope. We're going to use Keck. And there's a sort of fisheye picture of it down here at the bottom. And Keck is 10 meters in diameter, and that gives us a really big area for collecting all those red photons. And we're going to use a really big instrument called LRIS, that stands for Low Resolution Imaging Spectrograph. And so it's an instrument of the kind that Emily talked about earlier. It's a spectrograph that spreads the light out so we can learn about what the objects look at, like quasars look like at different wavelengths. And so there's a picture of LRIS here down here on the right. And to give you some scale for how big it is, up here at the top is a picture of the good side of our intrepid instrumentation manager at Keck and a colleague of his, and they're standing in and on top of LRIS trying to work on something. So LRIS is the kind of instrument where you sit inside it to work on it. It's so big. And you also get a nice view here of the realities of one of these instrument projects, which is that great big super scientific snarl of cables and wires and stuff like that, which all make these instruments go. And what this project that I'm going to tell you about is going to do is put a new really big and specifically really thick detector called the CCD in LRIS to make it more sensitive to red light. So what is the CCD? CCD stands for charged coupled device, and it's a detector made on silicon, the same silicon that makes the processor in your computer or your phone. And it's a detector, silicon detector for catching light. And I've got a picture here of an old school commercial charge coupled device. It's that little black square up on the upper left there. And it's the CCD detector in a digital camera, which is a little bit old fashioned now. The detector in your camera phone is similar. It's not a CCD, it's something called a CMOS detector, but it's also made out of silicon. And a lot of what I talk about here with red light and detectors would apply to a CMOS detector too. But the ruler on top shows you how small this CCD is. It's less than a centimeter across, so less than a half an inch across. The detector we're gonna put in LRIS is quite a bit bigger than that. Here's a picture of it, or one just like it, and the hand holding it gives you some sense of scale. It's a little more than 2 inches across, so pretty big in area, but the most important thing about it is that it's also really thick. It's a big chunk of silicon in there, and that's what makes it good at catching red light. So how does this work? Well, you have light photons coming from an object in the sky, like a quasar, a black hole from far away near the beginning of the universe. And those photons come in and get collected by a telescope. The telescope picture I've got here is a picture of the Shane 3 meter on Mount Hamilton, which is my excuse to give another shout out again to all the fire crews and all the firefighters and all the staff who worked so hard to save Mount Hamilton and of course everything around the local area. One of the great things about Mount Hamilton is you can do test projects there. And so in fact, one of the very first places that these thick CCD detectors were first put on the sky was on an instrument at Mount Hamilton. And it's one of the important things we get to do up there is try out new stuff. And so it's really great. And we're incredibly grateful that we still have that laboratory to use even after the fire went through and we had a close call. So, photon comes in, gets collected by the telescope, goes into a spectrograph, and that light gets dispersed so that we not only get an image of that quasar, but we can see what it looks like at every different wavelength that we can see. The spectrum gets captured by our CCD detector, and what we end up with is the data that lets us show how much light that quasar is putting out at different wavelengths. So we get a spectrum of the quasar. And if I zoom in on that spectrum, it's a plot of how much light the quasar is putting out as a function of at different wavelengths. And over here on the left, where the bluish light is, you can see there's not a whole lot there. The spectrum is pretty much down near zero. And as you move over to the right, you get to the red light, and you see this giant peak over here. So the quasar is putting out a whole bunch of light, but it's all on the red side of the spectrum. And so if we want to be able to catch the light from this quasar, which is coming from us from less than 1 billion years after the Big Bang, we've got, so less than 10% of the age of the universe, we've got to be able to catch red light. And that's what we're going to do with this new detector. So how does this work? How is it that we can use these silicon detectors to catch light? We use something called the photoelectric effect, which lets us use the electrons of silicon atoms to catch photons. So a photon from an object like a quasar comes in, gets caught by the telescope, spread out by the spectrograph, and eventually it lands in the CCD pixel. So this is once it lands in that pixel, if it's got enough energy, it can give a boost to an electron from a silicon atom in that pixel, and then that lets it get counted up a signal in that pixel. And so you put a whole bunch of pixels together and you count all the light that lands in all those pixels and you get an image. And just to sort of zoom in on that, there's a picture on the right here from the Hubble Space Telescope taken with a different CCD camera of a nearby galaxy. Beautiful multicolored picture. But if you get back closer to the source, there's a zoomed in picture here on the left of that same galaxy from an image straight off the CCD detector. And it zoomed in enough that I hope you can see the squares of the individual pixels. And those squares that are bright, those are the pixels that have a lot of photons land on them. And we're able to give electrons a boost and get counted as photons in the pixels. And the ones that are darker are ones where fewer photons landed in the pixels. And so that's how you build up an image of one of these CCD detectors. And so the trick about catching red light is that not all photons are the same. If you work your way across the spectrum here from blue to red, blue light photons have plenty of energy. And so it's really easy for them to give that energy boost to the electrons from the silicon atoms and free them up so that they can be counted as photons in the pixel. But as you work your way over to the right, to the red part of the spectrum, the energy of the photons goes down. And so because they have less energy, it's way less likely that they're going to be able to interact with an electron of a silicon atom and give them that energy boost so they can get counted. So how are we going to fix this? How are we going to make it more likely that that red photon is going to be able to give an energy boost to an electron so it gets counted? And the answer is we add more silicon, so that there's more of a chance as that photon comes through and lands in the pixel, it gives it more of a chance to interact with an electron before it falls out the other side. And when I mean thick, I mean seriously thick. These new detectors are 500 microns thick. That's 0.5 millimeter. That's big enough for you to see with your eyes, which is not usually the kind of thing we think about when we think about silicon. And to give you a comparison, a normal CCD detector of the kind that might have been in that digital camera, or maybe is the sort of silicon thickness that you get in a CMOS camera in your camera phone, is 16 microns. So these new LRIS detectors we're going to put in are a factor of 30 thicker, and that gives us way more chance to catch those red photons. And it's a sort of funny thing to think about, where we're making a silicon detector and we're trying to make it as thick as possible. And usually when you think about cool, exciting things in silicon, smaller is better. Right? Moore's law is based on the idea that transistor size for silicon processors, like in your computer or your phone, that transistor size is going to shrink over time. And that's what gives us faster computers, cheaper computing hardware, right? So usually when we think about silicon, we think about things getting smaller being better. But if we want to be able to catch red photons, what we need are thicker detectors, more silicon. We need to build a much bigger silicon detector to do this. And so these are really extreme detectors. We've got these, and the shapes are actually, because we want good resolution, we actually want them to be small in area, the pixels, but we want them to be really thick. So the shapes are actually more extreme than the tallest skyscrapers we know how to build. These 500 micron thick pixels are still really small in area. And so they make this really extreme shape, but that's what gives us the opportunity to catch these red photons without giving up our resolution, the sharpness of our images. So we're gonna get this detector in the instrument sometime in the coming winter. And these projects don't do themselves. And I've got some photos of the team up here, the people who are doing the engineering and helping make sure that we get the instrument we build the instrument that we said we were going to build. And so I get to work with really great people to put these new detectors in LRIS and to be able to catch the red light from amazing objects like like quasars. The picture down here is a zoom in of a really high redshift galaxy. And again, it also has had its light redshifted because it's so far away from us, and you can see how red it is in the photo compared to the other galaxies. These are the kinds of things that we'll be able to find once we're better at catching red photons with LRIS when we get this project in there. So yeah, it should be a lot of fun. We're looking forward to getting it to the telescope and being able to do great science. So yeah, thanks.
Great, thank you. Let's see if there are any other questions. So one from the audience is, so germanium next, and also it's a big sky. How do you pick where to look?
Oh, those are both really great questions. Germanium would be super exciting. If you've got a detector we can try out, I know the way up to the top of Mount Hamilton where we can get it on a telescope. Yeah, new technologies for detectors are really, really exciting because that's what lets us observe more wavelengths, and that gives us access to more of the physics of everything from exoplanets to quasars and how the universe works. So yeah, new detector technologies are great. They're always fun to try out. We always learn new things. It's a big sky. How do we know where to look? There are other projects with other cool gadgets that instead of focusing on individual objects or maybe a handful of objects are taking images of the whole sky in different parts of the spectrum so that we can not only get images, but tell stars apart from galaxies and measure how red or how blue they are so we can figure out how far away they are and use that kind of information. And sometimes some of these projects are taking images over and over again. So not only can we find galaxies and find quasars and measure how far away they are and what they're like, but we can see if they change. And depending on what kind of science you want to do, you use all that information to try and decide what you want to take a spectrum of and learn even more about individual objects. So there's a whole big ecosystem of tons of cool gadgets in astronomy taking great data so we can do lots of science.
Nice. Okay, another one. What are some of the first science cases that you plan to go after?
So there are lots of really great red things. So quasars is one of them, and one that I know Alex knows a bunch about. Other cool things are really cool stars, because cool stars and are stars that just about made it to become stars. And then you can look at other objects called brown dwarfs, which are stars that didn't make it to turn on nuclear fusion. And so understanding that transition is really interesting. And also it tells us how small can a star or an almost star be? And that tells us something about how star formation works. If you go down toward even cooler things, there are planets around other stars to look at. Yeah, all kinds of interesting red stuff. And I've, and blue things are cool too. It's just that this gadget is particularly about making about being able to observe red things. So that's what I've been talking about. But, yeah.
Lots of things to look at, definitely. And I guess this is for Emily or Connie. Connie, you're with us now. What's the most expensive thing you've seen broken?
Ooh. The most expensive thing I've seen broken is a secondary mirror. And that happened while I was a student, and I didn't break it. But one of the things I learned was that when something like that happens, the right way to react is to take a deep breath and figure out how to fix it and figure out how to not have it happen again. And if you get everybody thinking about the future, then there's no point in pointing fingers about how it happened. You just make sure it's not going to happen again. So, and that really stuck with me as a lesson for sort of how to handle things like that in the future. And it also makes you, seeing your colleagues behave like that made me braver, because it meant that if I did mess up, it wasn't going to be the end of the world and they weren't going to fire me. And it's more important to get the work done than to be paralyzed by not being able to do the work. So, yeah.
Oh, that was a wonderful answer. And how many of these skyscraper pixels are packed into a single thick CCD?
Oh, that's a great question. Bigger is better in this dimension also. So the one we're going to put in LRIS actually has 4,000 by 4,000 in one direction and 4,000 in the other direction. So 16 million pixels, which, you know, isn't really a big number when you think about, you know, gigapixels, but it's 16 megapixels. So yeah.
Wowie. Then I have a question for you. How many instruments have you worked on, I guess, over the course of your career, and which has been your favorite?
Oh,
favorite.
I'm not. It's been fun. I've been able to work on a bunch of different things, which has been really fun.
Mm.
And I've always learned a lot from all of them. And I always have a soft spot for the instrument that I worked on as an undergrad and a grad student I kind of grew up in, which is the imaging camera for the Sloan Digital Sky Survey. So I'll give you that one. It's hard to pick favorites though. They all have aged me a little bit, but they've all been a lot of fun. And yeah, it's always a great experience to work on them. I as Emily said, I agree with Emily. It's a huge amount of fun to work on these instrument projects.
Nice. Wonderful. I think that's all the questions from
Thanks a lot for the chance to talk.
Yeah, thank you so much for joining us.
You bet.
Have a good night. All right, and for our audience, now I'm going to put you all on the spot, finish up our quiz questions. So I'll show those to you, and remember you can put your answers here we go. Put your answers on the YouTube stream or write it on a piece of paper, however you want to share that with us. So our number 3 question: in August, which radio observatory was damaged to the point of halting observations? In August, which radio observatory was damaged to the point of halting observations? Hint, it is shown in the image, I believe. All right, next question. What was the cause of the damage to this telescope dish? A hurricane, B, a meteor, C, cable, or D, aliens? What was the cause of the damage to this telescope dish? A, hurricane, B, meteor, C, cable, or D, aliens? My money is on aliens. Can never go wrong with aliens. Okay, and our question number 5. Our historic Lick Observatory was spared by the fires. What year did Lick Observatory first begin operation? Again, our historic Lick Observatory was spared by the fires. What year did Lick Observatory first begin operation? And then our final question, surf's up. Big gravitational waves detected by LIGO and Virgo just made the news. What 2 astronomical objects collided to make waves? A, a man-made black hole. B, 2 black holes. C, our galaxy and Andromeda. Or D, aliens? Again, surf's up. Big gravitational waves detected by LIGO and Virgo just made the news. What two astronomical objects collided to make waves? Wow, a man-made black hole. Can you imagine? Can you imagine aliens? Well, I think you can imagine. Okay, so send us those answers. Take a picture with your answers. Take a picture with your ice cold beverage. And then some actual astronomy in the news. We'll take a little break, and then I'll give out the answers to all of the quiz questions after this. So some exciting astronomy in the news, very much related to that last question, was that record-breaking gravitational waves revealed intermediate mass black holes. And this was a huge mystery in astronomy for a very long time, that we could detect smaller sort of stellar mass size black holes in like the tens of solar masses, like 10 times the mass of our sun. And then we could detect an very, very, very massive black holes, like supermassive black holes, such as Sagittarius, A star, that's at the center of our galaxy. And there was this gap in the middle of that, including masses from about 100 to about 100,000 solar masses, or 100 to 100,000 times the mass of our sun, that we were not detecting. And so this LIGO detection is huge, because one of the black holes that was a part of this merger was in the hundreds of solar masses kind of mass range. So that is extremely, extremely exciting news. So definitely look at the link that we provided in the comments of the YouTube stream and read a bit more about that. Okay, are you ready for the answers to the questions? Let's see how you all did. Okay, so question number 1, the March equinox. This looks different. Ushering in the spring season in the Northern Hemisphere. On this day, the sun stands directly over Earth's A, North Pole, B, ecliptic, C, equator, or D, South Pole. And for an equinox, the sun is directly over the equator. So hopefully you put C. All right. Number 2, derived from 2 Latin words, equi and nox. What is the significance of the equinox? And during the equinoxes, both hemispheres receive equal amounts of daylight between the northern and southern hemispheres. Yes, good. Thumbs up, thumbs down. I can't see you, but pretend that I can. Number 3. In August, which radio observatory was damaged to the point of halting observations? That was Arecibo. Unfortunate. And 4, what was the cause of the damage to this telescope dish? And that is a cable. That is wild. It reminds me of stories of, roller coasters malfunctioning and the cables like doing damage and all this kind of stuff. And number 5, our Lick Observatory was spared by the fires. What year did Lick Observatory first begin operation? And that is 1888. Not gonna lie, I did not know the answer to this. So I hope you all know your Lick Observatory history a bit better than I do. And number 6, surf's up. Big gravitational waves detected by LIGO and Virgo just made the news. What two astronomical objects collided to make waves? and that is 2 black holes. I might have given you the answer when I was looking at astronomy in the news. So let us know how you did. I hope you all got 100% because I know you are all astronomy geniuses out there. So again, I think that's all that we have for this evening. I want to thank Emily Martin and Connie Rockosi again for joining us this evening. Their talks were absolutely amazing. I feel like I learned so much about instrumentation and kind of what they do on their day-to-day and the really exciting stuff that they're working on. So I want to thank all of you for tuning in and joining us this evening. And I want to thank the entire Astronomy on Tap team for just being absolutely amazing and a great team to work with, a great support system. And I do want to share the theme for next month's Astronomy on Tap, and that will be How to Look for Aliens, the Science of Searching for Life on Other Planets by Jonathan Fortney and Peter Gao. So make sure to join us next month to learn about the search for aliens and studying more about exoplanets. All right. I think that's all we've got for tonight. Thanks again, and I hope to see you all next month. Have a good night.